Hey everyone, let's jump right into today's explainer. We're going to be looking at a hidden conflict that's unfolding right in our own backyards, the massive and honestly often invisible water demands of modern data centers. If you care at all about your local community's resources, this is a topic you absolutely need to have on your radar. Imagine this: a severe drought hits, local reservoirs run low, and you're suddenly slapped with mandatory residential watering restrictions. But just a few miles upstream, a massive industrial facility is still gulping down millions of gallons a day to cool its servers. You've got to ask yourself, why? Why are you being penalized for watering your vegetable garden while they get a free pass? It's a profound question of resource equity. To really unpack this, our explainer is broken down into 6 quick parts. We'll start with the tech versus town conflict, figure out exactly why these data centers drink so much water, and then walk through 3 real-world case studies: retrofitting for drought, handling the intense heat of AI, and utilizing wastewater. Finally, we'll wrap up with actionable ways to protect local water equity. All right, kicking things off with Section 1, the tech versus town conflict. Let's look at what actually happens when massive tech infrastructure drops into regions that are already struggling with water stress. You know, the sheer inequity here is wild. Imagine being told you literally can't wash your car or water your lawn, but you look at the horizon and see industrial cooling towers continuously blasting plumes of evaporated water into the sky. It raises major environmental justice and public health concerns, especially when tiered pricing penalties hit local households first. Meanwhile, massive industrial users seem to just operate without limits. Moving right along to Section 2, why data centers drink water. We really need to understand why these massive buildings are tapping into our municipal water in the first place. Let's break down the science. It essentially all boils down to the first law of thermodynamics. Every single watt of energy a server uses turns directly into heat. To keep from melting down, those servers essentially have to sweat to cool off. The industry measures this using a metric called WUE, or water usage effectiveness. Basically, it shows how much water gets evaporated to remove that heat. And here's the tricky part. Lowering energy use often means spiking water use. It's a really delicate balancing act. To put the scale of this problem into perspective, a standard 100 megawatt data center using traditional evaporative cooling can evaporate anywhere from 500 million to 1.5 billion gallons of water every single year. That's a staggering amount. We're talking about the annual water usage of thousands of local households, just vanishing into thin air year after year. But listen, it absolutely does not have to be this way. The solutions we're covering today are pulled directly from professional engineering curriculum from PDH Direct. So we aren't just tossing around theoretical ideas. We're looking at proven, highly technical blueprints that actual engineers use to manage hydrologic risks and keep these facilities running without draining the town dry. Okay, Section 3, Case 1, retrofitting for drought. Let's look at what happens in the real world when a town's water supply actually starts running dangerously low. Picture a sprawling 300 megawatt hyperscale campus. Originally, it was built to rely entirely on municipal drinking water. But then, a brutal multi-year regional drought hits, and the local government mandates a massive 25% cut in industrial water use. The facility was completely caught off guard. They were quite literally facing server shutdowns if they couldn't adapt fast. So what did they do to avoid a total operational disaster and stop stressing the town? Engineers rapidly rolled out a 4-step hydrologic mitigation strategy. First, they optimized their water chemistry to recycle water more efficiently. Second, they retrofitted hybrid cooling, letting the plant run in a dry mode when the weather cooled down. Third, they started piping in reclaimed wastewater. And finally, they built 8 million gallons of on-site storage to give them a buffer so they wouldn't lean on the local grid during peak drought days. And the results were completely incredible. This multi-phase retrofit slashed their dependence on the community's drinking water by a massive 40%. They kept their servers fully online during a severe water stress scenario, proving that proactive drought contingency planning saves both the data center and the local reservoir. Let's shift gears to Section 4, Case 2, Taming AI Heat. This introduces a whole new, highly intense threat to the mix: artificial intelligence. Look, AI processors are powerful, but they run insanely hot. We're talking rack densities rocketing from a standard 20 kilowatts up to 80 or even 100 kilowatts per rack. For this specific enterprise facility, that kind of intense heat meant a projected 55% spike in evaporative water consumption. If left unchecked, that would have absolutely devastated the local community's water access. So how did they tackle it? Instead of just slapping on bigger cooling towers and evaporating more water, they completely rethought their architecture. They implemented direct-to-chip liquid cooling, literally capturing the heat right at the source. This allowed them to switch their outside heat rejection to a hybrid dry cooling system. And thanks to smart controls reading the outside weather, this entire facility can now run 100% dry, completely waterless, for 8 to 9 months out of the year. The impact here is just jaw-dropping. By switching to liquid and dry cooling, they achieved 70% reduction in evaporative water use. It just goes to show, AI doesn't have to be this unstoppable water-guzzling monster, as long as engineers prioritize water resilience right from the get-go. All right, Section 5. Case 3, the wastewater solution. This one is probably the most inspiring example for municipalities who are focused on long-term sustainability and protecting their residents. Here we have a rapidly expanding 180-megawatt campus. But instead of waiting around for a drought to trigger a crisis, they proactively partnered with the city. They knew that competing with local residents for clean drinking water was a huge reputational and operational risk, so they actively sought an alternative before breaking ground. They pulled off something brilliant. They inked a 20-year agreement and essentially funded a 3.8-mile dedicated pipeline to bring in tertiary treated municipal wastewater. They set up heavy on-site filtration and UV treatment to clean it up for their equipment. They literally took the city's wastewater liability and transformed it into an industrial cooling asset. That leaves the clean, potable water right where it belongs, with the households. The final numbers here are fantastic. An 82% reduction in potable water demand. They effectively eliminated their threat to the community's drinking supply, permanently securing both their own operational future and local water equity. Which brings us to our final part, Section 6, protecting local water equity. Let's talk about how communities can actually champion equitable resource management when these massive projects come to town. If you're a community leader or an advocate, you now have the playbook. There are 3 primary engineering methods that balance industrial cooling reliability with crucial municipal water conservation. Number 1, mandate hybrid or dry cooling architectures so they aren't constantly evaporating water. Number 2, require directed-chip liquid cooling for AI to capture heat efficiently. And number 3, strictly enforce the use of reclaimed or alternative water so they aren't drinking from the exact same tap as your community. You know, we really don't have to accept the old way of doing things anymore. The professional standard of care for engineers has evolved. They are now professionally obligated to design infrastructure that respects climate realities, anticipates droughts, and actively avoids draining local aquifers. If a design threatens local household water access, it's fundamentally flawed. So, I'm going to leave you with this final, provocative thought to take away from today's explainer. Are your local leaders asking these tough engineering questions to protect your water right now? Or are they just waiting until the next drought hits tomorrow? Knowledge is power, and now you've got the blueprint to demand better. Thanks so much for diving into this with us.